Hello everyone. Welcome to the presentation on meter constant, errors and adjustments in single phase induction type energy meter. In this video lecture, we are going to see the meter constant and what are the nameplate details of a single phase induction type energy meter and what are different types of errors we see and how to adjust the errors. How do we go for compensation of those errors? By the way, I'm Swati Pulasa, lecturer in Electrical and Electronics Engineering, Sanjay Gandhi Government Polytechnic, Adilabad. Let us have a recap on our previous video lecture, which was on construction and working of single phase induction type energy meter. Coming to the main parts of single phase energy meter, we had a driving system by electromagnets M1 and M2. M1 was having current coil which carries current proportional to the load current. M2 was E-type laminated core which was having pressure coil in the middle limb of the E-type core, and the current through the pressure coil was proportional to the voltage across the load. And coming to the moving system, it is an aluminum disc that was attached to the spindle, and we have a braking system by two permanent magnets which form a C-shaped look, and we have a recording system, worm wheel arrangement, or we also had a dial type, window dial type arrangement. Now you can see the single phase induction type energy meter construction. This is the E-type laminated electromagnet M2, which has voltage coil in the central limb. To adjust the flux produced by this to be in quadrature with the voltage across this coil, we use copper shading rings. We can adjust the position of the copper shading rings. Similarly, we have a U-shaped laminated silicon steel core M1, which had current coils which are connected in series and then series to the load. So they carry the load current, hence the flux produced is proportional to the load current and also in phase with the load current. And this is the moving system which we were discussing, the rotating aluminum disc. It was supported by steel alloy shaft, and we have pivot here, and we have a pinion here for gear trains to dials. Maybe the recording system may be a worm wheel, or we can have a dial window type of recording display system. Hope this was a very good recap on the construction of single phase energy meter. Coming to a few important points, let us have a revision on that too. Series magnet produces flux phi1 in phase with load current I. Shunt magnet produces flux phi2 which lags behind voltage by 90. Actually, it may not, but with the help of copper shading bands, we adjust the resultant flux phi2 to be in quadrature with the voltage across the pressure coil. These two fluxes induce EMF in the aluminum disc because the aluminum disc is a conductor placed in a varying magnetic field. Hence, by Faraday's law of electromagnetic induction, we should be having EMFs induced in the aluminum disc. One because of phi1 and another one because of phi2. Say they are E1 and E2. Now the aluminum disc is having a large surface and a very good thickness. Hence, it is like EMF is having some closed path to close the circuit. Hence, you will be finding some circulating currents flowing, and those circulating currents is what we call as eddy currents. Hence, the aluminum disc will carry eddy currents I1 produced because of phi1 and also I2 produced because of phi2. Now there is interaction between flux phi1 and eddy current produced because of phi2, which is I2. Similarly, flux phi2 and eddy current produced because of phi1, which is I1. So because of the interaction of phi1 I2 and phi2 I1, there will be a driving force produced which make the disc to rotate. Now the braking torque is provided by braking magnet, which will be having two magnets diametrically placed, and we can adjust the position of the braking magnet, which clearly states that we can increase or decrease the speed of the aluminum disc. The speed of rotation of the disc depends on actually the power, but because for domestic purpose or for industrial purpose, we are going to have voltage constant. Hence, it is directly proportional to the load current. The rotation of the spindle is proportional to the power of the load. As the energy As energy is power into time, a cyclometer and registering mechanism are included. The deflecting torque is proportional to the power. The braking torque is proportional to the speed. Hence, the speed is proportional to the AC power. So, the total number of revolutions. Now, if you integrate the above equation that I am showing right now with respect to time, then the total number of revolutions in a given time is obtained by integrating speed within the limits of the time. That's what. So left hand side, we are going to have total number of revolutions in a given time, and right hand side, we are going to have energy. Here, let us see the nameplate details of a single phase induction type energy meter. So you can see an image of a single phase induction type energy meter. There, what we can see some window, and through this window we can see a number dial. So you can see it is rotated, and each number dial is connected to each of the gear, which is in turn connected to the pinion. Now we have an aluminum disc here shown. So let us see what are the nameplate details. It is of course displayed on the meter, but let us see one by one. So we have supply voltage displayed, full load current displayed, frequency, meter constant. What is the meter constant? It is in terms of number of revolutions per kilowatt hour. So let us cross check if we have these things mentioned in the practical induction meter, which is induction meter, energy meter, induction type energy meter. So here you can see, apart from the display, you can see the voltage. This is a single phase type. It is mentioned here, model number there. Now 220 is the supply voltage or voltage rating, and 10, 20 amperes. We can have the current coil, that is, we have two limbs of U-shaped core, and we have two current coils, but they are connected in series. We can also connect them in parallel to increase the current rating. If so, then we can operate the same meter for 20 amperes. If they are connected in series, we can operate them at 10 amperes. Now we have the 50 hertz, that means a frequency. And you can see 600 R. Small r means revolutions. 600 revolutions per kilowatt hour. So this is what we have discussed here, the last point. And we have the meter number with year of manufacturing 2008 and 071288. This is the number. In this way, we have nameplate details of induction type energy meter. Getting to the next slide, let us discuss more about the meter constant. So the number of revolutions made by the disk for 1 kilowatt hour energy consumed. Kilowatt hour, in other words, can be termed as unit. 1 kilowatt hour is 1 unit. So if you say 1 kilowatt hour energy consumed, it means 1 unit energy is consumed, or vice versa. Now a meter constant is number of revolutions by kilowatt hour. This is capital letter K, which is meter constant. Please note it down. Okay. Now we will go for an example of this K. Here K can be 750 revolutions per kilowatt hour. So let us try to find out, solve a small problem here. Just try out this one. We here in this, we have an energy meter, has meter constant of 1000 revolutions per kilowatt hour. The energy recorded by it for rotation of 25 revolutions of the disk is. So your disk rotated through number of rotations of 25. After those 25 revolutions of the disk, how much energy is consumed by the customer? So we have a meter with meter constant 1000 revolutions per kilowatt hour. And now the disk starts rotating and it has rotated to 25 revolutions. Now, how much power energy is consumed by the customer? That is the question. I'll give you 2 minutes. Please try to solve it on your own. You know the meter constant. It is mentioned in the units also. Meter constant is revolutions per kilowatt hour. Okay, please do it. Okay, let me solve it for you. So let us write down the given data. The given data is meter constant, which is 1000 revolutions per kilowatt hour. Energy is recorded by 25 revolutions. So now we have R as 25 revolutions. How many kilowatt hours? Meter constant, which means it is going to be constant for n number of revolutions. So for this given data, say we have around x kilowatt hours for this condition. Taking this data, what would be meter constant? It should be revolutions, which is 25 revolutions. And what is the energy consumed? We don't know, so we take it as x kilowatt hours. So if you consider this condition, and then the meter constant should be 25 revolutions by x kilowatt hours. Now, whatever might be the condition of the number of revolutions, meter constant should be same. Hence, it is called as constant. So, I should, this 25 by x revolutions per kilowatt hour should be equal to the 1000 revolutions per kilowatt hour. So, let us write the same. 25 by x should be equals to 1000. Both the sides we have revolutions per kilowatt hour. Now from this we have to find out x. So x would be 25 by 1000, which is 0.025 kilowatt hours. This is one way of a simple way of solving the problem. We can do the same thing in another way also. So the constant says that for 1000 revolutions, 1 kilowatt hour is consumed. But then for 25 revolutions, how many? So more is the number of revolutions. So you have, if more is the number of revolutions, more will be the kilowatt hours consumed. So if you have consumed more energy, then more will be the number of revolutions of the disk. Hence, it is directly proportional. So you can use direct proportionality concept here. Again, then you will get this answer as 25 into 1, 25 revolutions into 1 kilowatt hour by 1000 revolutions. So you have answer only in terms of kilowatt hours. Again, 25 by 1000, which should be 0.025 kilowatt hours. This is how we arrive to the solution in two different ways. You can select any way of your choice and your ease. Please note down the solution. Now, after going through the problem and solving it, let us move on to the next slide. So we will enter into next topic of a video lecture, which is common errors in single phase induction type energy meter. The first one we'll just list down. First one is phase errors, and the other one speed errors, friction compensation errors, creeping error, error due to temperature variation. So we see phase errors, speed errors, friction compensation errors, creeping error, error due to temperature variation. Let us see all the errors one by one along with its compensation. First one is phase error. Let us see the cause of the phase error. So basically where the phase is important, we have seen that the current coil carries the load current because it is connected in series. So the flux produced by the current coil will be in phase with the load current. So no problem with the phase in with respect to the flux produced by the current coil. But the pressure coil has a bit less resistance, and of course it has a very good amount of inductance, but it has some small resistance, because of which the flux produced by the pressure coil may not be in exact quadrature with the voltage across the pressure coil. That is the cause. This is the reason. The flux of the shunt magnet does not lag behind voltage exactly by 90. So the torque is not zero at zero power factor. The torque is not zero at zero power factor. This is an important reason for the phase errors. So for zero power factor, torque will not be zero, and thus we'll get incorrect result. Aluminum disc rotates faster at lower power factor. These are few causes and results of phase errors. The causes are pressure coil has small resistance, torque is not zero at zero power factor. So, and also the flux is not in quadrature with the low voltage across the pressure coil, which is nothing but the load voltage. The result of the phase errors is the aluminum disc rotates faster at low power factor loads. So when the power factor is low, aluminum disc will rotate in a faster pace. How do we compensate? How can we avoid these errors? One is we have to maintain the flux in quadrature with the voltage. So it can be done by adjusting the copper shading bands. We have already discussed in the constructional details again in this video lecture. that we'll have copper shading bands in the central limb below the pressure coil, and we can adjust the shading bands so that the flux is maintained in quadrature with the voltage, and hence we can compensate the of errors due to this reason, which is phase errors. So we can change the position of the shading bands, which is on the central limb of the shunt magnet. The shading band or rings is also known as power factor compensator. So it is called as power factor compensator. This is important. Let us go to the next error, speed error. Error in speed of the meter when tested on non-inductive load. Speed of the meter is either fast or slow. So for non-inductive loads, the meter is either fast or slow. So this is what we call as speed error. Non-inductive loads means it may be either pure capacitive load or capacitive dominant load or resistive load. For these loads, the meter is either fast or slow. For this, the compensation is by adjusting the position of the brake magnet. We can adjust the position of the brake magnets and we can avoid the speed errors, because brake magnet position, if you uh, insert the brake magnet towards the aluminum disc, the braking torque is going to be more. The speed of rotation of the aluminum disc will get reduced. So that manner we can vary the speed of the meter or the aluminum disc. Movement of the poles of the braking magnet towards the center of the disc reduces the braking torque, TB. Now after that, friction compensation error. So let us see the cause of friction compensation error. Unwanted braking torque is produced on aluminum disc due to frictional forces at disc bearing register mechanism. So we have pinion on one side and pivot on other side. So though our moving system is light, still we can have some friction at disc bearing and register mechanism. So unwanted braking torque is produced on the aluminum disc due to frictional forces at these two places. Hence we have friction compensation error. How do we compensate that? For this compensation, we have to make ratio of shunt magnetic flux to series magnetic flux large, which means the shunt magnetic flux should be very high compared to series magnetic flux. So the ratio of shunt flux to series flux should be large by adjusting position of shading bands. Shading ring on the shunt encloses the flux in the limb. This produces eddy current. So the phase displacement between enclosed flux and main field in the air gap is produced. A small driving force is exerted on aluminum disc which compensates the friction. Now we'll see the other error, which is a creeping error. Creeping error. Creeping means slow but continuous rotation. Creeping error reflects in this way in an induction type single phase energy meter. How? It resembles something like this. There will be slow but continuous rotation of disk in the absence of load current. Even though we do not have any load running, the disk will be rotating slowly but continuously. This is what we call as creep. So the error because of this is termed as creeping error. So what is the reason? Because of the friction error, we do compensation. If that compensation is overdone, that will be the reason for the creeping error. So over friction compensation is one of the cause and one of the reasons which causes creeping error. And stray magnetic fields. We have external magnetic fields. If your energy meter is placed in external magnetic field, then there is every possibility of rotation of the disk, though there is no current, load current flowing through it. Another one is mechanical vibrations. Mechanical vibrations can have the shaft move or the disc moving, rotating. The voltage supply being excess of normal value. If the voltage is more than the normal value, that can also cause aluminum disc rotation, slow but continuous, even though there is no load current. Now, how to prevent the creeping error? Proper adjustment of friction compensation, which should not be overdone. There should not be over friction compensation. Two holes are drilled diametrically opposite on the circumference of aluminum disc. So if let me draw. If this is the aluminum disc, see this is the shaft. Now we need to drill holes diametrically opposite on the circumference. That means to this end and diametrically opposite. If you take a diameter here to this end. Both should be of same diameter. Like this, if this is the aluminum disc, this is the shaft, this one and this one. These are the holes. This is how we have to drill two holes in order to reduce sweeping error. What happens if we do this is, if we don't do this, then this causes distortion of the field. So we will have distortion of the field. In this hole, there won't be any eddy current flowing. So field is not going to be the same manner as we had a normal aluminum disc. So there is going to be distortion of the field. And hence we cannot have the slow movement of the aluminum disc because the field itself is not uniform. It prevents rotation when one of the holes come under the one of the poles of the shunt magnet. And let us see the last error, that is error due to temperature variations. These are small as various effects produced tend to neutralize each other. Causes are increase in temperature will introduce errors, increased resistance to the eddy current path. It reduces the deflecting torque and the braking torque, which means the eddy current is going to be small. Hence, the deflecting torque will get reduced and the braking torque will get affected. Increases resistance of shunt coil, causes small current to flow. Hence, the deflecting torque is reduced. Due to temperature variations, the resistance of the shunt coil will get varied. Hence, total effect is neutralized. That is the reason why it is mentioned that there are small as various effects produced tend to neutralize each other. So one effect is trying to neutralize another effect. So like increase in resistance will reduce deflecting torque and also the braking torque. Like this, if temperature increases, the resistance will get reduced. If temperature reduces, the resistances will increase. So increase in resistance of shunt coil, it will cause small current flowing through the shunt coil. Hence the deflecting torque will get reduced. Already there is going to be more resistance for the shunt coil, more inductance for the shunt coil, and resistance we try to bear in a bare minimum condition. And to achieve the quadrature flux to the voltage, we have arranged the copper bands. Again, because of temperature variations, if resistance increases, current or the flux magnitude will get reduced and thus the deflection torque will get reduced. So let us try to summarize. Please note down the table. So if we summarize, we have different errors that we have discussed. Error 1, which is phase error, it causes shunt magnetic flux. So it is what happens if this error comes and how the error comes. You know the meaning of the cause, reason because of which the error is introduced, and how do we compensate. So this table is formulated in such a manner. First column will show us the error and what are the reasons for the error is shown on the cause, and how to compensate the error is shown on the third column, compensation. So first one is phase error. Shunt magnet flux does not lag voltage by exactly 90 degree, which is an important requirement. So how can we do it? How can we compensate it? By adjusting the copper shading bands. The next error is speed error. Error in speed on non-inductive loads. That means when we have non-inductive loads, the disk will rotate either fast manner or slow manner. So we can compensate the error by adjusting the position of braking magnet. If we observe that the disk is rotating with faster rate, then we have to slow down the speed of the disk. We can do that by moving the braking magnet towards the center of the aluminum disc. If we observe that the speed of the disk is slower for non-inductive loads, then we can move the braking magnet away from the center of the disk. The other one is the friction compensation error. This is because of the friction. So the reason is unwanted braking torque on the aluminum disc. So how are we having unwanted braking torque on the aluminum disc? Unwanted braking torque means the torque that opposes the deflecting torque. So one thing is friction. So at the friction we have, because of friction, it also opposes the movement of the disc. So if you want to compensate it, we have to adjust the shading bands accordingly. Another one is creeping error. So the creeping error cause is overcompensation of friction, and its result is slow and continuous rotation of the disc at no load condition. So here I have to include one more thing, that the cause of creeping error is overcompensation of friction, and which results to slow and continuous rotation of disk even at no load. Then how do we compensate it? By drilling holes on aluminum disc. We have to drill two holes in opposite manner, like opposite to diametrically in opposite way, near to the circumference of the aluminum disc. What happens is we will have distorted magnetic field, and hence you will not feel the overcompensation of the friction because field is distorted, so there won't be much movement of the disc at no load condition. So this is one cause. One cause is overcompensation of the friction. The other one is vibration, as we have seen in detail in the earlier slides. Hope you are clear with the concepts discussed so far. So let us go to the next slide. So we'll have a quick recap on what we have covered in this session. We have seen the revision of construction and working of single phase induction meter, and then we have seen different meter constant, solved a simple problem on meter constant, and we have seen the nameplate details on energy meter, and also we have seen different errors, what are the causes of the errors, and what is the result of the error, and how to compensate the error. So the learning outcomes, optimistic learning outcome from this video lecture is the listener should be able uh, to know or explain the following about single phase induction type energy meter. One is nameplate details, meter constant, common errors in single phase induction type energy meter, causes and rectification of the errors, how to compensate the errors. So with this, we are done with the topic of the day. Hope you have understood the topics well. Thank you.